Wow, everybody's here almost. It's good. How's everybody doing? 5, 6, 7, 8, 9, maybe 10.
Amy won't be here. She's
That's right. That's right. Yes, thank you for reminding me. That's okay, because as I say, it's optional. So, what's new, everybody? Yeah, thank you. We're gonna start now. How's everybody doing? Smiles. I like that. Thumbs up. Or is it just one of those typical United American responses of yeah? How's it going? It's like hello, right? Hello. Nobody ever wants to say terribly. That's okay. Okay. Well, let's just drown our sorrows in classical test theory. Actually,
Generally, the substance of choice for me.
Say that again.
So that's not generally the substance of choice,
But you know, here's the thing: especially if you're in counseling, if you can get people hooked on it. Now, classical test theory, I probably think we need some type of way of cessation for most of it. But if you can get them hooked on the factor analysis, that I keep promising is coming. That's the time to do, right? Okay. So I'm going to try something a little bit different today because I'm going to pull up R. We're going to talk about R for the first time this semester, so that should be fun. I'm going to make sure I put my phone on silent because it would be bad form. I had a professor in grad school. They actually had cell phones when I was in grad school. And he answered the phone and he was like, hello? And I was like, oh, it's an emergency, right? And he starts talking in front of, in the middle of a lecture. And it was this kid at college and he's like, oh yeah, let me get my credit card. He's ordering, kid's trying to order a pizza. He's like, oh, I'll buy you a pizza.
Emergency.
So yeah, I have a phone that filters that out, hopefully. So if it rings, it is truly an emergency. Or, a spouse or child needs something. But anyway. So today, classical test theory, it's a lot of more stuff that I'm not really super happy about, but I want to give you kind of a perspective of what it does. The way I'm going to do this today is rather than put this full screen, because I'm afraid I'm going to screw up the technology. I'm just going to have the PowerPoint slides up like this instead. Probably won't matter. The other thing I realized with the last lecture, I'm going to touch on some of the parts of the slides, but a lot of the slides are there for your own reference. But many of you have taken classical test theory over and over and over again, right? So you don't need to know this. Let me tell you my philosophy in classical test theory. It's given and used often less the way that I'd like you to learn it. So think of it this way. Classical test theory is a set of restrictive assumptions on a factor model. That's how we're going to learn it in this class. So the times where you might use an instrument and add together item responses, that is a model that you're implying about your data. A very specific model. But the use of factor analysis can help you test whether or not that truly fits the data or actually holds with the data that you do. So there's nothing wrong with it in the sense that it's a testable model. If you believe it to be a testable model and you test it, and if you find that it does fit the data well, use it. That process, though, doesn't usually get done. So that's how I want you to start thinking about it. That's the big picture. Today, I'm going to wave my hand at validity. And then we're going to talk about reliability a little bit. And what the heck is up with alpha? All right? Any questions before we begin? No. At some point, I'm going to stop hating on things, I promise. I say that about my life. I've been told I'm one of the best critics. I had a professor in grad school who was like, you're really one of the best critics I've ever met, which is like a backhanded compliment, right? So that's why I have the job I have. But no, anyway. Okay. Other part I want to mention about classical test theory and why the assumptions might be there. So the factor model and the item response models and all the other types of measurement models that we see later on oftentimes take a larger sample to be able to do. Now, you may not have that larger sample, but you still want to do as good of science as possible. The trade-off with the complicated model against a very small sample has often been to put assumptions in. The more assumptions you put, the more the model will start to work with a smaller sample. And classical test theory might be what you have to do with those assumptions, but I want to teach you what the assumptions should be and how to put the constraints in, starting with the measurement model at first. Try that always. Don't just go here. I think that's where I'm going. All right, so let's talk about classical test theory. Classical test theory is effectively the theory behind what happens when you give somebody a test or a survey questionnaire. They give you responses that are numeric at some point, and you sum them together, the add stuff up model. Right? And once you get a score from adding things together, there are two big concerns that we usually lump together about scale scores. One is how reliable are they? So reliability, I'm going to read this off the slide, is the extent to which the instrument does what it's supposed to with sufficient consistency for the intended usage, or extent to which the same results would be obtained from the instrument after repeated trials. And we operationalize reliability, or actually calculate, we quantify it in several different ways, but it's always about reliability for what? If we go on, you've probably heard before, a test has a reliability. I mentioned this previous. It's not that the test has the reliability, it's what you're producing from the test itself, right? It's the number that you're giving to the person. If that number comes from adding things up, there's a method that we use for reliability. If that's not what you use, if you use the factor score, which I said not to do in EFA, but it's what we do in CFA a lot, there's a different way of using the reliability, but still reliability, it still means the same thing. It's how consistent should that score be. Have any of you taken multi-level models before? You've done that. If you're ever in a multi-level context, we also talk about reliability for different coefficients in a regression model. How reliable is the slope? How reliable is the intercept? So there's all sorts of reliability, and there's a big picture topic of it, which is essentially what proportion of variance out there does this thing account for? That's really what we're after, right? So regardless, you can get into the weeds of Cronbach or Spearman-Brown or whatever came after Cronbach, which we call omega, but other people call other things. But the bigger picture should be, it all functions the same. It's how you calculate what proportion of variance shows up in an analysis of the number. So, the second one, which I'm waving my hands at, validity. All right, what is validity? It's if you're going to call your score some label, that label is appropriate and accurate. Right? You measure what you intend to do. It is a measure of degree, and I will tell you these slides are somewhat incomplete, and you'll get a better treatment of this in, I know Billy Skorupski's 921, he covers a lot more than this. So there's, when you get into validity, and actually that's where we start, another way of thinking about this, validity itself, starting here, is that there's all sorts of these topics of validity. It's been around for decades, right? Making sure that the test score really is appropriate for it. And nobody said, if I wanted to see if you're able to get into grad school and I measured your height, and I said that's your score, probably not valid for getting into grad school, right? For a number of reasons. And there's all the labels that we've attached to it, right? The criterion validity, predictive validity, intended use, and you wrap it into a big argument. But one thing that I wanted to emphasize, there's another type of validity out there that no one talks about, but that's essentially what this class is about. And it's essentially assumptional validity, that when you give a person a number, that number is accurate. Right? We always say, the thing I've always had a problem with validity is it starts with the score. But do you realize how many assumptions have to be right to get that score to be accurate? Right? A ton, right? You always start with the score. It's like, hey, once I mentioned the height, your height is, if your height was our score that you had, like that was your GRE score. Like you went and take the GRE and they're like standing against the wall and they measured your height. Right? Be really reliable. probably wouldn't be valid, right? But that score, really reliable, no assumptions hardly needed, right? You assume essentially height's constant at some point or it fluctuates within some amount. You also assume that the measuring capability of whatever you stood against is accurate. And with physical measurement, that's pretty much the case. Certainly height. But for us, we're measuring things that don't exist. And so all those things that you ascribe to the score, like you ascribe to height, aren't there, right? What if you were to measure height with rulers where the inches weren't exactly an inch, or the centimeters, or however you want to do that? Like you were to put together building blocks, like of inches or centimeters or whatever your familiar unit is for your country and background, right? But the blocks weren't all the same size. That's what effectively we have here, right? Sort of randomly draw blocks of different sizes to try to put together inches and see what your height is. That's what the items represent. Each one of them measures it imprecisely. It's an imprecise measure of metric. So to me, this whole class is about one type of validity that never gets talked about in the validity texts, which is the score has to be accurate mathematically and numerically for it to even be interpreted for reliability or validity in the first place. How's that? There. That's my treatise on validity. I used to say validity doesn't apply to me, but anyway. Other ways to think about reliability and validity. Anyway, actually, any questions on that while I take a drink here? Has anyone ever mentioned that before when you talk about validity? Like to question the score itself, it always starts with the score. And you sort of say, well, how reliable is it and so forth. But those numbers are all off if the assumptions that go into it are off as well. Anyway, so another way to think about this, so if we think of classical test theory, we have this thing, observed score, right? The sum of all the items is equal to the person's true score, right? Which is their theoretical version of this factor or this trait, if we could measure it without error, plus error. And we can think that error can be random. Random error seems to compromise reliability, right? The more random error there is, the more fuzzy our measure is, the more your score isn't exactly the same every time we were to give it to you. Error can also be non-random, right? So non-random means some type of confound that's in the assessment itself, or some type of constant source of variation that shows up. It's that. Essentially, whether or not you are biased in some regard in your survey, I think is another way of putting it. That's sort of compromising, it is compromising validity, essentially, right? If you have a systematic bias, if you have a survey bias of some sort against some type of group, then that score is less valid for the group itself. So another way you can talk about it is reliability concerns how well you can hit the bullseye of the target, right? How accurate you are. And validity concerns whether or not you hit the target at all if you're arrows. You've seemed to have heard this before. Nobody's like, wow, this is earth-shattering. I'm not quite yet drowning your sorrows in this, but wait for just a moment. So more about validity. There's all sorts of ways of doing this. I'm going to skip these slides. Everything that you've learned before about it, critically important. But this class is about focusing on validity for the score. Right? So think about that when you go through it. Nobody talks about that usually. So we're going to move up past that. So in summary, critically important. But everything after the score applies to the things that you've seen before. And I can't give you a big enough treatment for that because everything we're going to do here is about the validity of the number itself. Now, to get into what we need to do, we're going to talk a little bit about some statistics. This is going to be reliability. We're eventually going to get into reliability, but this is going to carry forward with us when we get into CFA next week. What we're going to review here is variances and covariances. Fair enough, right? You're used to standard deviations and correlations, right? Seems to be a topic that we talk about forever. But covariance seems to be something that we never discuss or seldom. Now, the prerequisite for this class was multivariate, and I did a good job double checking. So you've had covariance before, right? You've seen it, sort of? A little bit? Okay. But let's talk a little bit more about it, because the basic unit of what we do in a lot of the statistics we use are built on covariance. Why is that the case? Well, I'll answer my own question. Anyone want to guess why we use covariance?
Because if you have like two like variables with different like scales, the covariance is the first one to start with. Then from that you will standardize it.
Well, not quite. It's assumptions. We have a lot of psychometrics. Classical test theory, certainly, a lot of classical test theory, not all of it. But the theory that underlies Spearman-Brown and the theory that underlies Cronbach's alpha, Cronbach alpha, depends on key assumptions. And the theory that starts with confirmatory factor analysis depends on key assumptions, and that's that our items are continuous. And we throw another step on there in CFA in that we describe our continuous items as having a normal distribution. We have error that follows a normal distribution. Oftentimes, in the classical test theory, y equals true score plus error, we lump this assumption about the distribution of error following a normal distribution. Well, it turns out, when you assume that the normal distribution for error, and what we'll see next week, the normal distribution for factor itself, you're making an implicit assumption that the items follow a normal distribution. And when you put a bunch of items together that follow a normal distribution, actually the assumption is a little bit stronger than that, we assume that they all follow a multivariate normal distribution. Familiar with that from multivariate? That is why it's a prerequisite for this class. In the multivariate normal distribution, it's essentially this normal distribution in multiple dimensions, right? There are two key matrices of parameters. One's a vector, the mean vector. The other one is a covariance matrix. And that is it. We use covariances because they are directly implicated in the normal distribution. They're direct there. If we weren't using a multivariate normal distribution. If we weren't using a multivariate normal distribution, the emphasis on covariance goes down considerably. That's the key. So, in the multivariate normal distribution, there's this covariance matrix and this mean vector. And a lot of what we're going to do in CFA is the CFA model prescribes exactly what these should look like. And that's how we test our data. We effectively say, if your assumptions are true, if you think that your factor structure is accurate, your covariance matrix should look like this. Right? Your mean vector should look like that. And actually, the mean vector we usually forget about. And if it doesn't look like this, then your assumptions have to be wrong. That's what we're after. But we start here in classical test theory with covariances because they underlie Spearman's or Cronbach alpha, essentially. So let's talk a little bit about covariance. So backing up, scale is important. When you have a variable, like some type of variable in a regression analysis or something you're measuring, the units of that variable are important. So let's talk about my height. I keep measuring height. That seems to fit everything. I'm going to use inches because I haven't traveled abroad in a while. I'm just going to go with the one place on Earth that still holds on tight to this system. So my height, I'm 70 3/4 inches tall. How's that sound? That's right about where I'm at. So just a little over 6 feet tall. And so the inches themselves, if I say I'm 70 3/4 is my height, you would say, what's the scale, right? What is the scale of that? Well, the units of that are in inches, right? So then you would talk about, okay, so what is my height compared to the distribution of people who would be like me? What about, middle-aged, balding male professors, right? So just trying to figure out a nice cohort to compare myself to here, right? It's hard to call, I turned 40 this year. It's hard to call myself middle-aged, but I am pretty much over the top. But the idea that you'd say, okay, let's talk about, where's the mean height, right? That's also in inches. And there's some mean, I don't know what that is. But then there would be a standard deviation of height. What does the standard deviation represent? I'll ask you that question. What's a nice, easy summary for what the standard deviation is?
standardized measure?
Not quite.
Percentage of the sample.
Also not quite, sorry.
Excuse me, can you repeat your question?
What interpret the standard deviation?
It's
Variable.
That's what we also call it.
the variability from the mean.
Well, let's take it, and Michael?
I was going to say prescribes a normal range.
Almost. What I'm going for is this. Let's take a look at the formula, right? The standard deviation formula is the sum of y minus y bar squared all over n. We'll call it n minus 1, like this, right? And actually, I'm going to do this right here. This is the maximum likelihood estimate of the standard deviation, which is biased for finite samples, but as n goes to infinity, it's biased. Why I'm doing that is because I want you to think of this. If the mean is the sum of x over n, what is this thing? I'm trying to make an analog. It's like the mean deviation. That's right. It's not quite the mean absolute deviation. It's like the average distance someone would be from the mean in the sample, right? That's what a standard deviation means. For me, I think that it describes variability and all this, but it's like on average, how far is an observation from the mean? That's how I look at it. Now again, with n minus 1 there, and because we have a square root, it's not exactly that because we got all the nuance of it, but conceptually it's like the average distance. But that average distance is described in inches. If it's an inch, if your variable is there, it's the units of the variable, right? If I take the standard deviation and I take off this square root, I effectively get this variance, although I have n over here instead of n minus 1. The variance is still an average, right? It's the average squared distance a person's height is from the mean height, right? So it's in inches squared, right? And this is the part of units I want you to think about. When you talk about variances, when you talk about units, you're talking about squared inches. You're talking about the squared value of a variable itself. If this were an item response, if it was item 1, everybody's item 1 score, what circle they put on the Likert scale you used, it would be the squared distance in squared Likert units from the average for the item itself, right? So that's what a variance happens to be. So the variance has units, and those units are units squared. The standard deviation has units. So when we get into CFA, this becomes important because a lot of our metrics involve units of some sort. And within the unstandardized, we call unstandardized results, often deal with those units directly, right? What am I talking about? If I were to say height y equals a regression to predict y with x, beta 1 has units, right? It tells me the units of y for each unit of x, right? It's like units of y over units of x. What units are they in? Well, they're in the unit of the variable itself. We usually talk about in terms of standard deviation. So let's talk about covariance then, right? Covariance is essentially the average product of the deviation from each variable and its mean. It's just really impossible to understand and comprehend. But think of it this way. If we called this unit squared because we took the square function here, right? If we had a variable and we were multiplying the square itself, I could rewrite this as y minus y bar times y minus y bar, and it would be the same, right? That's the variance. And so I called this squared inches before. But let's imagine I'm marrying weight. That's not a good thing. Anyway. Yeah, sorry, I apologize in advance. Your instructor sucks. This class is going to be terrible. But that being said, if you think about it, this is inches squared. But if I change y over here, if I had y1 and y2, right? And y1 was inches and y2 was pounds, that would be a covariance. Now n minus 2 is on the slide, but this is the maximum likelihood version of it with n, right? But similarly, I would describe a covariance in units of inches times units of pounds. So the covariance is this odd scaled variable that makes no sense. And I would say, if the covariance of a sample was, 380,000, it'd be 380,000 inch-pounds. What? You don't run around talking about that, right? Covariance is what we would call unstandardized because it has units attached. It has units that might be some value otherwise. Now, the correlation, though, takes the covariance, which would be like inch-pounds, and divides it by things that have units as well. Anyone ever takes chemistry? There was something called stoichiometry. I failed chemistry in high school. I really did. I have my high school transcript. You can see the F. I remember this thing. I did take it in college. I did all right there. But I remember this thing called stoichiometry where we were canceling units and change things, right? Well, here, if I have a covariance and it's in inches by pounds, right? That's the covariance. If I divide it by something that's in inches and times something that's in pounds, I cancel these, right? And essentially cancels out the units. That's what correlation does. It becomes unitless because you effectively take the inch-pounds from covariance in my example and divide it by something that's in inches, dropping the inches off, times something that's in pounds, dropping the pounds off, and now we get a number that has a uniform range that's standardized. How's that sound? So standardized can be thought of as removing units. The other way of thinking about it is homogenizing what the unit is, because a standardized variable has a standard deviation of 1, right? So another way of thinking of this is that the correlation is a covariance between two variables with a standard deviation of 1. They both have a standard deviation of 1. So, okay, that's my treatise on covariance now. Next week we're going to come back to that because we're going to end up we're going to want to take something like this. If I'm predicting if this was inches and this is pounds, right, then beta 1, the units of it are inch-pounds, right? But if I want to standardize it, we do the same process. If I want to make this where there's no units, I'm going to have to multiply by the units of pounds and divide by the units of inches. And that's the process of standardization that shows up. So just saying this now is foreshadowing what's going to come up next week. Next week it's going to be, this is a factor and this is an item, but we want to standardize coefficient for certain reasons, and that's where that's going to show up. Are we cool? Different way of thinking about it? Okay. Now, if you have binary items, so that's all the continuous items, and that's awesome, and we all love that. When you have binary items, though, it gets even more messy. Binary items are items that can have a 0 or 1, like 2 categories, right? We call them binary because we often give one category a 0 and one category a 1 as a numeric thing. That's an arbitrary choice, but there's 2 categories to it. Dichotomous is another term that we use. The item mean, as you know, would be the same way we find it before, the sum of y over n. In this case, would be the number correct out of the total number of items. The item variance, though, is that item mean times 1 minus the item mean. And why this becomes a headache for what we're going to do later on in this class is that because the mean and the variance are tied together. You know the mean, you know the variance. In the multivariate normal distribution that we're talking about here on the board, or what we were describing before, there's a mathematical property of it where you can prove and show theoretically the mean is uncorrelated with the variance. Right? The mean and variance in the multivariate normal, the mean vector and the covariance matrix are independent. Meaning, you know the mean, it tells you nothing about the variance. Right? You know the variance, it tells you nothing about the mean. And you can think about it for height, right? If I knew the mean height was 68 inches for my cohort, it wouldn't tell me anything about how much variability there was, right? Could be the case that we have a former basketball player on staff and we have someone who has dwarfism on staff, right? The mean's still 68. Or it could be that we're all about the same height, like Billy and I are right about the same height. Yes, yeah.
Just to cover maybe,
Yeah.
because maybe I missed the point, but when you say that there is the mean and the variance as are independent of each other in the multivariate.
And independent in the multivariate normal, that's right.
Okay, so it will cancel the degree of freedom because we will not use in the denominator, like n will be, because
Well, we can still calculate covariance, but it's going to be a function of the mean. Right? Same thing goes here, right? This is the variance, p times 1 minus p. We can still calculate, and actually if you go back to this formula, if you use it with binary items, it would give you the variance. But the variance you can show is p times 1, the mean times 1 minus the mean. So it's what you know about the statistic that tells you about the other part that you're looking for. I think that's where what I'm calling. There's also the mathematical property of what statistical independence means. It really means the distribution of each of these is set, right? So hope that helps a little bit. Where this applies to us also is classical test theory to get some of the things that we want. For instance, if we want to go and say the test score, figure out the standard error of the test score, and you put a confidence interval around the true score, we're going to assume a normal distribution. But every test that we're going to use has some type of ceiling and some type of floor. So it could be the case that we form a confidence interval and the upper bound or lower bound goes beyond the ceiling or floor of the test. That's the first interaction of what we see. So it's part of the variance and so forth. This is sort of setting it before. Okay, how are we doing? All right. So what happens when we sum up a bunch of items together? Like if we had y1 plus y2, if we wanted to figure out what the mean of the sum is, it's the sum of the means. That's what this is telling you. Now, there's a notation that we use in mathematical statistics called this expected value. It sort of has an algebra into itself, so I won't get too much into it because I don't think it's super important. But just understand that the sum of the sum of the items, if you're talking about the mean of the sum, it's the sum of the means. But when it comes to variance, it's not the sum of if you have a sum of items, the variance of the sum is not exactly the sum of the variances, right? You do have to add the sum of the variances, but you now have to tack on the covariance between the items as well. Right? And you can think conceptually, where did the 2 come from? Well, we want to sum up all the cells of the covariance matrix. Okay. So in classical test theory, the unit of measure is the test, and we're trying to quantify reliability. And this is the reliability formula to focus on, right? When I say, you know, getting into the weeds of reliability, you have to worry about, like, is it Spearman, Brown, or is it Alpha, whatever. They're all trying to do this. What the variance of the true score is over the total variance. So what does that represent? Let's, again, this is a conceptualization more than anything else, but let's try to visualize this. If right here was y, right? And let's imagine I have this beautiful, see how well I am drawing this. There is the distribution of true score, right? If there is no error variance, this is the only distribution to worry about, right? The true score and the total score have the same variance, they're the same. But what happens if there's an error variance? It means that for each point, it's not good, let's try this. For each point on the true score, right, for each point on t, we're going to add to it some type of distribution, some type of score around it, right? And so what's going to happen is it's like we have this like a normal distribution around here. And so what's going to happen is our total score distribution is going to be widened because all this error that's being added by that, you know, by having variance of error, right? So in classical test theory, it's like saying for every point on the true score, we're going to add a value that comes from a normal distribution, and each of those normal distributions are going to have the same variance or the same standard deviation. Right? So what that effectively does is take what we've observed and widen it. So reliability is always going to be, usually use a rho, that's a terrible lowercase rho, but we're going to try that. Lowercase rho is going to be variance of true score, or actually I'm just going to call this variance of trait. Right? This is the thing we're trying to measure over variance total. That's it. That's always reliability for almost everything that we do. Variance of what we're interested in over total variance of what we've seen. Okay? Let's go here. So let's take a look. If we look at our true score plus error formula in classical test theory, we see that if we take the expected value of y, where that expected value means it's we want the mean of y, it's this, and because we have a sum over here, we take the expected value of the sum. That means it's the sum of the expected values. We expect error to have a mean of 0. So what we're after, we say the average or expected value for the score is, in the long run, the true score, right? But the problem is that holds in the long run, right? If we were to test a person over and over and over again, we don't do that. Maybe some of you do. I don't do that. We don't have time to do that. Time is short. So instead what we do is we try to conceptualize, and this is sort of the advances of, like, you know, somewhere between 1919 and 1950. We say, what is the variance of y? Well, we know that's the variance of true score plus the variance of error. Now, we normally would have the 2 plus the covariance here, but we allow the true score and the error variance to be uncorrelated. We actually force them to be uncorrelated. So that means this goes away. There's a 0 correlation, there's a 0 covariance. So we say the variance of y is the variance of true score plus the variance of error, so therefore we can get reliability by saying what proportion of the variance of total is due to true, right? So, but we have to have 2 scores to do that, really, or at least that was the first conceptualization of it. How can we measure error with only 1 score? Well, test-retest came about. Right, they go give you 2 tests, and then they talked about alternate forms. If you have 2 forms that are supposed to be parallel, you can give those to people, or split half, which you do again. But then we finally get into more practical versions, which is something about the features of the items themselves. If we make some assumptions about how the items are working, then we can quantify the internal consistency, right? And that's where Cooter-Richardson 20, which is, ever heard of that one? KR20 is alpha for binary items. It's named for the authors of the paper, and the 20, it means it came from the 20th equation in the paper. So it's, I think, in 1936 or something, 1939 is the date of that. Somewhere in the 1930s is when this happened. I'm sorry, my studying is not up to par, but hopefully that helps. But what internal consistency does, it makes some assumptions about how the items work together to come about with not having to do something about test-retest or give 2 versions of a test to a person, right? Either test-retest or splitting forms or having alternate forms or something like that. So that's where that comes from. No, let's not do that. Alternate forms, nope, let's not do that. Who cares? Ta-da. Internal consistency, there we go. That's really what we do these days. We don't really care about the other terms. And what happens is if the assumptions of this hold, that it actually equates to what you'd find for test-retest or split half. And so the nice thing about using an alpha or KR20 or whatever is that so long as the assumptions hold, we can make that work. So internal consistency for quantitative items, those are things that are supposed to be continuous, although we use Likert scale on that for the most part. We have a Gutmann-Kronbach alpha. Gutmann really came up with it in 45, Kronbach 51. But really, Cooter and Richardson sort of did that already with the KR20. It's described in multiple ways. It's the mean of all possible split half correlations. It's an internal consistency measure. Again, my mentor Rod didn't like that, but other people do. Whatever. It is the lower bound estimate of reliability under a couple of assumptions. So what's lower bound mean? It means this is sort of the worst it gets if these assumptions hold, right? That being said, these assumptions don't hold, there's another assumption that doesn't hold there. There's a couple different assumptions we use. We say that all items are what we call tau equivalent. Tau equivalent means they're equally related to the true score. Right? That's sort of what we see when we assume the sum. Each item sum, we don't multiply it by any other factor. It's just the raw item itself. The other assumption we have is that all item errors are uncorrelated. Right? So somehow, whatever error comes with the item, how far off it is not, if you're off on one item, it's not related to how far off you are on another item. There's a third assumption that really should be on here that I don't put, that nobody ever talks about. I should have it here, which is the items are unidimensional. They measure one score. Right? Because if they measure more than one score, if they don't fit that one score model, what happens? It's no longer a lower bound you have. It's actually an inflated estimate of reliability. Right, imagine you think you have 50 items, but only 30 of them measure the dimension you're after. Reliability is going to be calculated on 50 items. That's going to look really good compared to 30, right? So that is it becomes an inflated estimate if unidimensionality doesn't hold for the score. That's the big problem with it. Now, if unidimensionality holds, it might get better than reliability might be better than that. Yeah, great.
So assessing unidimensionality is why we need CFA. So we look like CFI, TLI.
That's exactly it. We have to go and find an assessment of whether or not what we're adding together follows a unit. It follows one factor altogether. Ugh, can't talk.
So, like, because of the inflation, my thinking is that this is related to the idea of the statistical equation that is proposed or come from like the it's called, I think, Spearman prophecy.
Yeah, Spearman-Brown, that's right. Spearman-Brown actually has a more restrictive assumption. It's not tau equivalent items, it's called parallel items. And so not only are all items equally related to the true score, all items have the same amount of variance as well, or error variance as well, which is a much more strict assumption. And so what you'll see is if you find that the items all measure one dimension, so the big thing, the big assumption is dimensionality. If you are able to identify that they're one dimension, the Spearman-Brown estimate, first of all, parallel items and tau equivalent items rarely happen in practice. Rarely, right? Parallel items was 1919, that was when that came out. They said, if this is the case, this is what happens. And then by the 1950s or late 40s, where we're saying, it's probably not the case. Let's weaken that and do tau equivalent. And then when we get to the 1970s, we weaken it again, and we say, well, but what if they're not even tau equivalent? What if they're differentially related to true score? So anyway, let's imagine they're all unidimensional. And you can calculate all three of those statistics, Spearman-Brown, alpha, and then the reliability that I'm going to teach you next week, which is called omega, which does not assume tau equivalency even. They're going to be ordered. Spearman-Brown will be lower than alpha. Alpha will be lower than omega. And that's what we talk about for the lower bound. But that's only if one dimension. That's right. Okay. So where does alpha come from? I get that from my kids all the time. Dad, where does reliability come from? Let me tell you. Sorry. There's this thing called the covariance matrix that you have to sum up, and that's usually where they do it. Never mind. Anyway, it's the sum of items that you have to calculate that. I'm not going to talk about that much because alpha, if you take a look online, I have an example that I put up that's in R Markdown to show you this. I can't share the data with you, but I can show a little bit of what's going on. I'm trying R Markdown for one of the first times to try to teach with in this class. Have you ever seen Markdown in R? So in RStudio, you can build something like this text file. Of course, I can't build it for you now. You can build this text file, but you can embed in it R code. So it becomes what we call an R notebook. And then, I should have updated this before, but what happens is you push a button, it takes the text that you've written and it's called knitter. It knits with the R code, and it creates an output file that's HTML or PDF or whatever. So when you go on our website, you'll see an example, and it'll be an output file, and it will be, here, I'll just pull it up. If you go here, oh, I didn't put it up. That would help. Actually, no, that's not it. We're over here in classical test theory. There it is, right here. It looks like this, right? So there's R code interspersed within text. And what it does is it allows me to show you what I'm doing with each of my R snippets for what we're doing. But you should also be able to download the code itself. And if you have your own data, you could use the code with your own data. I can't give you these data because they're someone else's available. You can show all that itself. You can download the code or hide the code. But it helps me in R. It's not going to work. Never mind. It helps me in R because if I had got it to work, I can actually run snippets of code individually. And you can see the text around it, then you can push play on it, and in the file itself, below the text, it'll put the output. So it'll put text around an output. There you go. So, yes. So, next time. My apologies. But on that file, if you want to do alpha in R, the package I use typically is something called Psych, PSYCH. It's by Bill Merida, who's at Northwestern. He's a member of SMEP. We talked about SMEP a lot. But Bill Revell, actually. Bill Revell is his name. He made this. It's very nice. It does nice things with classical test theory and a couple other stuff that you'll need. It's a nice output format. You can see for this data set that I have here, it spits out your reliability, your raw alpha, gives you standard deviations and so forth. It kind of gives you an upper bound for it. Does all the things that you'd want. It slices, it dices. Yeah.
Psych has data sets, correct?
It does, yeah. You can load in its own whatever data set's in it to make how it works. So yes. But here is part of the issue with alpha. How do you get alpha to increase? More items. What type of items? More items. Just more. So long as the items are correlated, right? Because basically, alpha, you can think of it as the number of items times the average correlation. That's one way of thinking of it. So the more items that you have, so long as they're correlated with all the other items, that's alpha. Alpha is not a measure of model fit, also. Right? So here's an example. What do I mean? This is a very bad piece of output. But if you have an average inter-item correlation of 0.2, to get to an alpha of 0.8, well, here, with 10 items, your alpha is 0.714. That's if the items are correlated like 0.2. For 0.4, they're much higher. But here is why alpha is not an index of dimensionality. It's not a measure of model fit. Here are two correlation matrices. On the left, it's a test with 10 items. On the right, it's a test with 6. And you'll note if we were to calculate alpha off of both of these, alpha would be the same, 0.81. In the correlation matrix on the left, all the correlations are the same, which is essentially what would happen if a unidimensional scale were to fit tau equivalency. On the right, there's a segment of items, a block at the top that are intercorrelated to 0.6, a block at the bottom that are intercorrelated at 0.6, and the off diagonal, they're correlated to 0.3. That's what would happen if you had a 3-item scale that was 1 dimension, another 3-item scale that was 1 dimension, and then they had some type of correlation between the two scales themselves, two measures. This is a multidimensional correlation matrix. Great.
So what if you have like 3 items is minimal to have a factor? So how do you assess the unidimensionality of like a straight up 3-item scale?
It is always unidimensional in a factor model. It fits perfectly.
Yeah.
That's exactly.
So, like the CFI and the TLI will be perfect, but how do you assess whether it's solid?
Um,
I mean, reliability alpha?
Let me back up. If you were to do reliability alpha, it would not actually fit perfectly. You could assess it because what you end up doing to calculate reliability alpha is effectively putting a constraint on the factor loadings. All the factor loadings are equal. And so you free up a couple degrees of freedom in that, and you can test whether it's tau equivalent. But if you didn't have alpha, there's another measure that we could use that's based on the factor loadings and unique variances. It's omega, and you'd use it. But yes, there's a group of people out there in the world who do structural equation modeling who are very concerned about model. Model fit, first of all, has to be everything. That's sort of your, mentioning your assumptional validity. When you assume there's one thing, one trait that you're summing the items across, that's the biggest assumption you'll make. That's why reliability depends on it. There's a contingent of people out there who go around saying, well, the way you shortcut that in CFA is to have 3-item scales. 3 items, 3 items, 3 items, 3 items. What happens with a 3-item scale? Bad reliability usually.
Usually, but what if you have like 0.8?
You can. It's possible. It can happen, and that's fine. That's fine. Yeah. What's your name, by the way?
Shada.
Shana, thank you.
So for test B, you said that there is 2 dimensions.
That's right.
So which items would you say go in each dimension based on that?
Items 1, 2, and 3 form 1 dimension because they're kind of their block correlations 0.6.
Okay.
And items 4, 5, and 6 have a similar block.
Okay.
And then off of that, because you can see 1, 2, and 3 don't go with 4, 5, and 6 because their correlations with each other are lower.
Okay.
And that's what typically happens. When you say that if you were to go into this thinking I have 2 dimensions, you'd want to see a correlation matrix that looks somewhat like that.
Is
Thank
that
you.
what they mean when they said like there is a pattern?
Yes, that's exactly it. What we're going to get used to doing, and this is why, now we typically swap out correlation for covariance. But what we're going to be doing is essentially looking at the covariance matrix, and seeing what an assumption of 1 factor or 2 factors looks like with it. When we get to CFA next week, that is really where our model fit depends on how accurate we reproduce this with our model. Other questions? All right. Is this a little bit different take on classical test theory that you've seen? So hopefully it's a little bit more different from what's going on. What do you do with reliability? Now this doesn't change. Regardless of how you quantify reliability, what you do with it doesn't change. Often what we do is we form a confidence interval for a test score. Right? Now we have to assume certain things about the test score to make this work with our sum. We have to assume that error follows a normal distribution. But if error follows a normal distribution, which is a often common assumption, I don't know how well we quantify it. I don't think it necessarily does when you get to the ceiling or the floor, but let's just say in the middle part of the test, then how we find a confidence interval, if we want to do a 95% confidence interval for a score, we take the score we give a person and we add plus or minus 1.96 times the standard deviation of error. Standard deviation of error is the reliability coefficient times 1 minus the total variance. Right? So what you can come up with, another way of looking at it is if you say the variance of true score is the total score times reliability, then the variance of error is what you observe minus the variance of true score. There's ways of doing it different ways. This gives you a nice standard deviation. And now for the next example, how many you all took the GRE? Here you go. Here's what if you believe what's reported about the GRE, this is what they're telling you the verbal ranges are for the standard error of measurement. Now you'll note these change. One of the things that they do is they sort of shrink it on either side because of the way they calculate this. This is sort of a shell game they're playing from ETS. But if you get a 500 verbal, this is the old scoring system, that means we're 95% certain your score is somewhere between 567 and 433. It's a pretty big range. How about math? Here's the one that kills me. 500 math, right? Your range is somewhere between 600 and 400 almost, right? You get a 4, if your true score is 400, you're like, wait, I need to do more math, or I need to take the GRE again. If your true score was 600, you're like, hey, that's probably pretty good. I want to get it, right? So think about what happens when you're taking the GRE, and we do this instinctively when it comes to test taking. If you get a low score, what do? Take it again. What are you bouncing around on, right? If your true score was 500, if it truly was, if your true value of the GRE is 500, it's possible you got like a 400 or a 410 your first time. Right? So you're going to take it again. Right? Okay. Boom. You got a 600. You stop taking it. Right? Or, okay, you got a 450. Take it again. So what happens? Right? You're essentially playing the game of chance if this is to be believed. The problem with this is twofold. Number one, the way they give you this standard error of measurement, they don't tell you what that is. They don't tell you that for your score. And because now the test has different blocks for different people, each 500 is going to have a different range for it because of the way they do their scoring. It comes from a factor score that comes from an item response model, and each factor score has a different reliability.
I can see that maybe, I'm not sure, but it seems that the reliability in details.
And that's the other thing. The reliability for the tail in most of what we do is much less because we haven't given you hard enough items or we haven't given you easy enough items. So we really don't know where you are. That is an artifact of how they are reporting reliability. What they do is they take a simulation. They basically say, let's imagine I have a person with this value of the true score. And then they run them through the process they take of the test. And it's all online. They know all the item properties. They essentially pretend the person's taking items. The item response model gives you a probability they would answer an item correctly. So they randomly generate a random number and they see which ones they get right or wrong. And in this case, they ran it through the computerized adaptive algorithm. So if they had a true score that was 700 close to the range, the algorithm only gives you up to an 800, right? So it compresses the range. There is a theoretical version of reliability that we could have given you that's not based on the compressed range that would be more accurate. But they don't want to do that because it would look bad. What we would see, now for the computerized adaptive test, you should see these are roughly the same because in the old GRE they were trying to make, the reason we do computerized adaptive tests is to shorten the test length, but effectively we can design how reliable each part of the test is. We'll get to that in a few weeks, actually October. But in the new version, because they're doing blocks of items, and each block may not have the same set of properties, you might see differential reliability with it. What you would normally see is that as we get bigger, as we get closer to the tails, or the ceiling or floor, our reliability gets lower, our standard error gets bigger. They don't want to show you that. So that just drives me nuts. So in admissions, I never use the GRE. And I won't use the GRE until they tell me the reliability precisely for each score they report. It is a shell game. It is terrible. I hate that you have to take it.
So it seems that you are implying that there should be a conditional error for each score.
That's exactly what there should be. And there will be. And there is, actually.
Yeah.
But they don't report it. And they don't report it. One of the rationales is, well, people don't understand it. True. But if people were to come to understand it, it would hurt their business. That's not my argument.
Is the SAT the same?
Yes. ACT, SAT. Now they're not reporting this. Each test itself has a guide to use of test scores. It's usually the GRE. If you Google GRE guide to use of test scores, that's where this came from. SAT will have one as well. Each of the tests that you take, often the big ones will have what they call a technical manual, and you can find this embedded in there. And the question is, okay, what game did they play to calculate reliability?
Is this what Lisa's article was about?
Lisa's, which article?
It's about like the GRE scores.
There was an article we wrote about this, yeah. So, okay. Binary items is Cooter Richardson. Okay, a couple other things I want to talk about that we're going to see coming up later on. We're going to quantify reliability a little bit differently, and the reason is, number one, reliability for what? That's what you have to be asking yourself, right? Up until now, all you've seen is summing up items to make the score. So the alpha, Spearman-Brown, and what we're going to call omega is still for that sum of items. But what if you want to switch over to factor score? Because the GRE, for instance, is a factor score. It's not a sum of items. Right? How do you quantify reliability there? So you have to keep in your mind reliability for what? What is this reliability for? And to me, it's the number you give a person. Right? Alpha and Spearman-Brown won't work on this. Right here. I actually use Cooter-Richardson 20, but even that won't work on it either because they're not giving you a sum score. This is reliability. They report reliability with something called the Cooter-Richardson 20 for the GRE, like the actual number they give you, but that's not valid because it changed. Each score has a different reliability. So reliability for what has to be there in everything that you do. When we get into what we're going to get into later for measurement, most of the time we do factor scores now. That formula still holds. We'll have an estimate of the variance of the trait. We'll have an estimate of the variance total. That little drawing that I have on the board still holds. So keep that in your mind. And when you're doing your own research, if you want to accurately quantify reliability, it's the score you're using. It's the score you're putting into the next model. It's the score that you're reporting to the client. It's the score that you're giving the person. It's the score that you're putting in your journal itself, in the journal article, or however you're doing. So the other part is because everybody is so locked in on alpha, like what do you call reliability when you get there? My default is just to call it reliability. Period. Right? That's reliability. Alpha enacts that with some assumptions. Spearman-Brown enacts that with even more strict assumptions. What we're going to learn about omega is that with other assumptions, right? The same thing that happens whenever we get to IRT, and that happens whenever we get to CFA as well. So I just call it reliability. I don't call it whatever formula for it. So if you call reliability and you put a coefficient or you put a range of coefficients, I found that usually works for everybody. They're probably assuming it's alpha, but just call it reliability. The other thing you can do is put a footnote and say how you calculate it. So. Okay, other questions on this? All right. Have I had to make you unlearn reliability for this at least a little bit? I'm trying to I want this to be like an unlearning process.
Uninstall.
Uninstall, every test has a reliability. Every score has a reliability. And how you calculate it is that. All right? And reliability is only true if what? Your assumptions hold. And actually, the score is only true if your assumptions hold.
So just to clarify, the equation you put there is that about the score itself, not the whole distribution, because this is what I understood.
That's right. If you have some observed total of that score, right? Reliability for it is how much variation is that is due to the thing that you're trying to measure, the trait. So.
If using CFA model, the reliability also calculated by this.
Now, in a CFA, if you're going to give reliability for a sum score, because a lot of people run a CFA to check the unit dimensionality and then go and add items up, that is something that looks a little bit more like alpha. But it's a sum, because it's a sum score. If you're going to give reliability for a factor score, you actually either set or estimate the factor score variance. That's the trait. And then each score has a standard error with it. So that trait plus the standard error is the total variance. Right? And so you can calculate that as well. So there are ways to do this for every method out there for it. But it's sort of the thing that, so this is the odd thing with me. I was fortunate in grad school that, I don't know if fortunate or not, but it was good for me because I learned all the new stuff and then I had to go backwards and learn all the old stuff, where I feel like most of the world learns this, like alpha, and then doesn't learn anything else. And so like learning how to talk about it is really a key thing. You just sort of, the concept of reliability is the big part. But remember, reliability only holds if your assumptions about the test hold. So, there. Okay. So there are two other things I want to calculate or quantify that come from classical test theory that show up in our measurement models as we go forward, and they're properties of the items. The first is something that we call item difficulty, which is really a terrible name. It's the item mean. It's not really difficulty, it's sort of backwards. But if you think about if you had a math test and you scored every item right or wrong, we would call the item difficulty the proportion of people who answered each item right. Well, it's sort of inverse. It's like item easiness, because the higher the number, the less difficult the item happens to be. But that's a measure that we use. So that's one thing, right? So it's an item, the item mean is the item difficulty. Cool? That still applies, by the way, in classical test theory, whether you're having a math test or you're taking, like, the MMPI, or, like, I feel sad today. Yes, no, right? The item difficulty of the sadness item. People still call it that. It's an item difficulty. What we'll see in factor analysis is, in CFA, there is an actual parameter for the item mean. We call it the item intercept, but it is the item mean. It is the difficulty. When we get to item response theory, we have a parameter that's actually named the difficulty of the item. And it's appropriately named, because the higher the value of it, the harder, the fewer people get it right. So, but item difficulty is one concept to know. Item mean. Cool? Means are no problem. The degree of difficulty is low. The other is discrimination, which, if we were discovering or rediscovering psychometrics at this point in time, psychometrics have been around for, I've read, thousands of years. Right? There's evidence of it in Eastern countries 2,000 years ago. Right? If we were rediscovering it now, we wouldn't call this discrimination, right? It's a terrible name for it. But what an item does, discrimination is talking about, is how well an item discriminates between people in the low and the high range of the trait. How well does it differentiate those people? Right? Another way of putting that is how related the item is to the trait. So you're starting to think here, where have you heard relationship before? Correlation, regression. Discrimination effectively is an item's slope. Like if the item is high discriminating, the slope or the regression coefficient, remember I mentioned before that when CFA, it's a bunch of regressions for each of the items themselves, where we're predicting the item score with the factor score. Well, that slope that goes on the regression, the thing that multiplies the factor, is the item discrimination. In classical test theory, we sort of have backhanded ways of figuring this out. I don't know about backhanded, the indirect ways of figuring this out. We often use the item total correlation, and how well an item correlates with the total score. Right? Whether we have the item as part of the total score or whether we take the item out of the total score is a common method of it. Just ignore all that. Forget about all that, because if you let me describe to you how classical test theory is CFA, or a measurement model with restrictive assumptions, then discrimination comes from that as well. Right? So we can quantify discrimination more accurately in the measurement model framework. Okay. Let's see here. What else do I want to say? Yeah, that's about it. Anybody have thoughts? I just want this to be different than what you've heard. It is.
In classical CTT, so the discrimination for all items should be same?
It is not. That's a good question. Under tau equivalent items, which is the assumption we use to get the coefficient alpha, yes. In practice, it's never the same. Right? So the assumption of discrimination, assumptions about it, sort of have this weird interplay with classical test theory in general. And if I could go on a tangent a little bit, so that sum score that we did, there's a way of doing that in factor analysis I'm going to show you, where we get a factor score that has a correlation of 1 with the sum score. It's not a different metric. That correlation is 1. So my argument is that with these assumptions, you're doing what you do when you add up items. And those assumptions have the same discrimination. It's actually what we call parallel items. Parallel items have the same factor loadings and the same unique variances. And when we set the factor loadings to be equal and we set the unique variances to be equal, all the factor scores we get out correlate perfectly with the sum score. And again, we're going to talk about assumptional validity, right? That's what you're doing. You're doing parallel items when you're adding up. The score itself comes from the assumption of parallel items. What happens if those don't hold? You start to see reversals in orders of the score. Someone who you thought was higher than someone else actually was the opposite, right? It's not a lot in the factor analysis world. Actually, the bigger difference is if your assumptions about normality don't hold. If you're using a normal model when you should be using something for categories, there's a much bigger difference. But yeah, in this weird interplay of what happens in classical test theory, it was basically trying to figure out, okay, this doesn't meet reality, but if we loosen this assumption, here's what we get, and we get alpha, right? But none of those hold anymore. So it's now we know a lot more about it. So depending on what you do, in practice, you use a reliability coefficient that assumes discriminations are all equal, but you calculate item total correlations, assuming they're not. Other thoughts, questions? Okay, I'm on time again. I don't want to keep you any later than I have to. Thank you. Once again, homework 0 due tomorrow night, if you haven't already done it. At some point over the weekend, I will put up the scores. Have a great holiday weekend. Try to do nothing, or as little as possible, or use the time however you like. Anyway, see you, everybody.
أنا حليت.